Good afternoon, good evening, good morning. Welcome to our Rigaku webinar, Sample Screening and Data Collection on Single Crystals with CrysAlis Pro. I'm your co-host, Joe Ferrara, and your host, Pierre Legamargores, will begin shortly. Go ahead, Pierre.
Thank you, Joe. Welcome everybody indeed. I'm glad that you're all there with us. So what we're going to go through today is how to use CrysAlis Pro to screen single crystals, calculate a data collection strategy on them, and start a data collection. So I'm going to first switch the video display here so that now on your screen you should see a live display of the inside of our system with the goniometer, the sources, and the detector.
If you look in the upper right-hand corner of your screen, you will see a square and a rectangle. If you click on that, you can switch between the PowerPoint slide in front of you and a larger view of the goniometer system, and then switch back to the PowerPoint view as well.
Thank you, Joe. So the live display on your screen should reproduce something like you see on the picture here. I would like to first remind everybody that we have been running this webinar since the beginning of April, and that if you go to the Rigaku webpage and go to the support menu here, there will be two links pertaining to our webinars, one for past webinars so that you can listen and watch those past webinars which have been recorded, and there's also another link for that will give you a list of the upcoming webinars. So like I just said, those webinars are being recorded. As for this one that we are running right today, it should be posted on our Rigaku webpage at some point in the course of next week. So you are welcome to ask any question you may have during the webinar. We'll just ask you to do that in writing, and you can do that by using the Q&A feature in Zoom by pointing your cursor to the bottom of the Zoom interface. You should have access to that Q&A feature. So the system we are going to use today is the XtaLAB Synergy-S. It is shown on the picture here. And so the specs of the system are listed on the table, in the table on the left-hand side. So you can see the dimensions of that Synergy-S, its width, height, and depth. The Synergy-S is based on microfocus seal tubes, and you have the choice of one or two sources among the copper, molybdenum, or silver radiation. So you can certainly just get or set up your system with one source at first and add a second source at some point later. There's no change to make to the configuration of the system besides adding that second source. So what we have for our system today is actually two sources. One here, if you see my hand here, one here at the front for copper and another one at the back for moly. So we have two separate beams, and from CrysAlis Pro I can choose one or the other. Following the seal tube or the source that is inside that chamber, you have the optics in here, and the purpose of the optics is twofold. First, it focuses the beam onto the crystal, which is already mounted on the goniometer head, but it also monochromatises the beam so that we get rid of most of the K-beta radiations. So the beam here hits the crystal, and that beam has a full width and medium height of 100 microns. It's actually slightly different as to whether you use copper, moly, or silver, but they are all very close to 100 microns full width and medium height. So what does full width and medium height mean? So here is a representation of an idealized shape for the beam. So the beam should have such a Gaussian shape. If you take the top of that curve, the maximum height here, and then go down to half of it, and at that level measure the width of the curve, or in our case the width of the beam, there is your full width at medium height. Now, the amount of intensity that comes through the full width and medium height
as shown by this box here, is about 50%. The other 50% come from the addition of what's left outside of the full width and medium height in the tail of the beam, on the left here and on the right. Now, given the overall strength of the beam, 50% of it is already quite a lot. Therefore, it is fine to start screening crystals that match the full width and medium height of about 100 microns. The reason for this is because smaller crystals will usually generate smaller, sharper reflections, which will improve the quality of the dataset.
Unless, of course, you have a weak crystal, and then you want to use as much of your beam as you can, but otherwise, for most of your samples, mounting and analyzing crystals that are about 100 microns big should be okay. So then in the middle here, you have the goniometer, and our goniometer is made of 4 axes with the kappa geometry. The detector here is put on a sled, and the sled itself is telescopic, so that the detector can back up all the way to the back of the enclosure here if you need to resolve long unit cell access. The detector that is usually configured with the Synergy-S is a hybrid photon counting detector from Rigaku, the Highpix 6000 HD. Turns out that today we have the Highpix Arc 150. This is really the same detector, it's just 50% larger. And as you can see on that video display, it is also curved. But otherwise, all the features are the same, including the pixel size, which is of 100 microns. So this is for the presentation of the system. I'm going now to minimize that window and jump right into CrysAlis Pro. So what I like to do before I even look at my crystals is actually come to the machine and look in CrysAlis Pro as to whether the current or the radiation that is currently set up on the system is the one I want to use. So currently we are using copper on the system. And indeed, this is the radiation that we want to use today. And I also like to take a look as to whether my cryo system is at the temperature that I want to use to analyze my crystal. So if you need to switch the radiation of your system, remember we have 2 here, copper and moly. So if you need to change the radiation, left click on that button that currently says X-ray copper, and then answer that question here that is asked to you by clicking on yes. If I clicked on yes right now, CrysAlis Pro would automatically turn off the source, switch to moly, and then automatically raise the power of the moly source all the way back up to 50 watts. The whole switch should take about 3 minutes only. Instead, I'm going to click cancel there. As for the temperature of the cryo system, so I am already at 100K here, but if you find it at room temperature, then you can control that from CrysAlis Pro as well by clicking or left clicking on the button that says cryo. So left click on here and then click on set. And in there, in that dialog, you have access to all the programs that you otherwise find on the temperature controller of the Oxford cryo system. So here, if you needed to cool down, you would select the cool program, implement your target temperature, and then click OK. And that would start cooling the cryo system to the temperature that you desire. So like I said, I like to do that before to even look at my crystals under the microscope. Obviously, for the cryo system to cool all the way down to 100K, you'll need anyway 20 to 30 minutes. So therefore, it's a good thing to check as to whether the machine is ready, even before you look at your samples. So here, everything checks out just fine. So I'm going to close the enclosure. And then I'm going to create a new experiment in CrysAlis Pro to start screening my crystal. So to do that, go to Start Stop, left click on Start Stop, and then click on Start New. The first thing to do is to center the crystal. So like I said, I already mounted a crystal on the goniometer head. The first thing I need to do now is to center the crystal. And to do that, I will push on the mount button here. As I do that, the video display of the crystal opens up. And as you can see on that video here of the system, the goniometer has also moved. And let me explain to you what happened here. So basically, the goniometer just oriented the pin on which I have mounted on the goniometer head and on which the crystal is mounted in a horizontal way. So the pin is now has the orientation shown by my finger here. So once the pin is in that orientation, it makes a straight angle with the crystal camera that is up here. So this is the red box here that is the crystal camera. So like I said, there is now a straight angle between the orientation of the pin shown by my left finger and the orientation of the camera shown by my right finger here. So here is that straight angle. And that orientation of the pin will allow me to center the crystal in the horizontal plane as shown by my left finger right now. And so in the perpendicular direction to the camera. So the way you want to center your crystal is always in the direction perpendicular to the direction of the camera. So to center my crystal, I will use this tool. You might not see it properly on the video display, but that tool is hollow. And I can set the tool onto pins that stick out, so to speak, stick out of the goniometer head. So I've got one pin here and another set of pin 90 degrees away from the first one. So one pin here and one pin there. There's also a 90-degree angle between them. It amounts to having an x-axis and a y-axis on the goniometer head. There's now a third pin on the goniometer head that will allow me to control the height of the sample, which is what I'm going to do now. I'm going to center the crystal into the beam, and to do that, I basically need to bring the crystal here that you see at the tip of that loop to the crosshair, the red crosshair. That crosshair represents the exact position of the direct beam. So I need to bring my crystal there. So I'm going to start here with the height of the sample, and I'm going to bring the sample up all the way up to that horizontal line. Then I'm going to center the crystal in the horizontal direction by, let's say, centering on what we will call the X direction first. So I'm setting my tool here on the goniometer head, and I'm rotating the tool so as to bring the crystal to the crosshair slowly and precisely. So I've already adjusted the height of the sample, centered it in the X direction. Now I need to center it in the Y direction, the Y direction being here. And as I just said a few minutes ago that I need to center the crystal in the horizontal way. So that means I need to rotate the goniometer head by 90 degrees and bring that direction into the horizontal plane. To do that, I click on the button that says 90, and that rotates the crystal by 90 degrees along phi. So now I can set my tool here again and center my crystal in what we will call, let's call this direction Y, the first one being X. Okay. So once you have centered along Y, this is good practice to come back and center or check your centering along X to see whether you need to adjust things a little bit here, which oftentimes you do. So here you must take all the time you need to properly center your crystal dead on with the crosshair. So because with crystallography, the devil is really in the details. So of course you want to mount a good crystal, but once you have mounted your good crystal, you really want to center it properly to the center of the beam, because this is where the beam is the most intense. Remember that the Gaussian shape I showed you before. So the tip of that curve is the center of the beam and the most intense part of the beam. Another thing that you can see here is that how small my crystal is, especially when we look at its side view. So the circle here, the red circle, its diameter is exactly 100 microns. So that circle represents the full width and medium height of the beam, as I explained before, 100 microns. But here you see I didn't even bother mounting a crystal that was as big as 100 microns. And I did that because I know that I have a strong crystal here. And as long as I have a strong crystal, which means that as long as I will have enough diffraction intensity, I want to use a smaller crystal. Usually a smaller crystal will generate smaller reflections and also sharper reflections. And therefore your I have a sigma statistics on the reflections will be better. And so the data set being better, your structure should be better as well. So this is for crystal centering. I'm going to close the enclosure of the system again, and then get out of this crystal viewing video display. And we're getting ready to start screening the crystal already. And let us take just a little break here, because we would like to ask you a poll question as to how you were trained on CrysAlis Pro. Whether you were trained by one of us crystallographers at Rigaku or by somebody else. So Joe will send you a poll question right now.
So on your screen, you should see the poll question. How were you trained? And either by a Rigaku application scientist, by your X-ray facility manager, or you acquired CrysAlis Pro for processing and taught yourself. So we're at about 60% compliance. We'll let this go another 10, 15 seconds. I'd like to get 80%. We're at 70 now. Just a few more. Very good. Okay. Wow. We're doing better than 80% compliance. Excellent. So I'm going to go ahead and end the poll. And you can see that 47% of you were trained by one of our Rigaku application scientists, and an equal number, 27 and 27, either were trained by your X-ray facility manager or you acquired CrysAlis Pro and taught yourself. Oh, I forgot to share. So now you can see the results. Thank you, Pierre.
Good, great. Thank you, Joe. So screening the crystal now. There are two steps in screening crystals in CrysAlis Pro. The first one, which is called screening, is a quick X-ray snapshot about your crystal, just to see if it diffracts, and if so, how much. This is just really simple and quick. It will collect 20 images in one single crystal orientation. Looking at these preliminary results, if you dim your crystal good enough, then you jump to the next step, which is the proper and fancier screening that is called pre-experiment. Pre-experiment will collect data in several crystal orientations. And so because we will collect data in different crystal orientations, the indexing will be better and more accurate. And therefore, the strategy that will be calculated from that better indexing will itself be better. So let's first take that quick extra snapshot and push and screen the crystal. So if I push the button screen here, so screening will start using an exposure time of 2 seconds. If you want to change that exposure time, this is when you click on that little arrow button that opens a more advanced dialog, and you can certainly change the exposure time here and implement whatever you want. Now, how much should you expose your crystal? Whenever you mount a crystal from the first crystal from a new batch for the first time? Well, I don't know, and you don't know either. So you have to start somewhere. You have no idea basically how much your crystal will diffract. So I think that on the XtaLAB Synergy-S, when you use the copper radiation, a good exposure time to start with is 5 seconds. It might be too long for many of your crystals, but for some others, it will not be long enough either. So 5 seconds is probably something, a nice starting point. If you are using the moly radiation instead, make it 15 seconds because moly is always a bit weaker than copper. Instead here, I will stick with 2 seconds and push OK and screen. And now the system will start collecting data on that crystal. So you see the goniometer here getting into position for data collection, the detector coming close to the crystal, and then the shutter opens up, and that data are now being collected. And suddenly we see diffractions, diffractional reflections on the screen. So if you look at the bottom of the CrysAlis Pro interface, you see the number of frames being collected within one run. So run here means one crystal orientation. So a total of 20 images are collected upon screening. And here it is. Now, what to look for to determine as to whether your crystal is good enough to continue with your experiment. So first of all, on the right-hand side panel, a concurrent indexing took place. I didn't do that. CrysAlis Pro did it by itself. And these are the unit cell parameters it found so far, with all three angles close to 90 degrees, and therefore the indexing algorithm thinks that at the moment that crystal has a primitive orthorhombic symmetry. Above that, you have reflection statistics showing you how many strong reflections were gathered throughout those 20 images, 116 here, and how many of these 116 were actually successfully indexed in that unit cell. So 114, which amounts to 98.3% of the reflections indexed. So obviously here, this is really good, but of course I chose a good crystal for this webinar. But don't get too hung up on these numbers, because at this point, indexing might still be wrong at this point, and that's totally okay. This is because we have collected only few images and only in one crystal orientation. So at this point, you may not get yet the proper indexing results, and therefore that percentage number might be a bit low. So instead of looking really just at the raw numbers, here is what you should look at. First, the actual number of strong reflections that the program saw on these 20 images. So we've got plenty here, 116. This is more than enough. Really, I would like you to see about 15 strong reflections there after your screening. So I'm just giving you rules of thumb. So about 15 reflections. If you don't see these 15 or so reflections, this is probably a good idea to come back to that advanced dialog and increase the exposure time. Now look also at your diffraction images and see how far away from the direct beam those diffractions appear. So the direct beam is underneath that shadow here, which is the shadow coming from the beam stop. So the direct beam is actually located somewhere underneath that round shadow. And this is around that point that those rings, which are the resolution rings, are centered. So the direct beam is somewhere behind that shadow. And so you want reflections to appear as far as possible away from that direct beam. And it would be good here to look to see diffraction of reflections already to about 1 angstrom. Again, if you don't see reflections towards the edge of the detector and away from the direct beam, this is again probably because the exposure time that you used here was not long enough. So go back in there and increase the exposure time. And then if you have to increase the exposure time even several times, so that's okay. Just increase it until you see enough reflections. Look further at the reflections also and determine how what their shape is. First, it's better if you have nice and round reflections like these here. It doesn't have to be perfectly round, but as close as possible to having round reflections. You don't want these reflections to be too elongated, basically. And something else very important, and I repeat, very important, you want these reflections to be single. You do not want to see double reflections or so-called split reflections, which would indicate that your crystal is either twinned or cracked. So let me show you a couple of examples of what I mean. Here is a first example here of split reflections, for instance. See, I've got split reflections here, here, and even weak ones there. So on that one image, I've got already 3 split reflections, okay? So that's no good. If you see just a very few of these split reflections throughout the 20 images of the screening experiment, that's okay. But here I'm already seeing 3 on one image, and and there are many more on the other images. So this is no good. Here is another example of something that is no good: elongated reflections like this one here. Okay, so that's really a badly shaped reflection. If I use this button down here to browse from one picture to the next, so here by pushing on this button, I'm gonna jump from frame number 1 to frame number 2. You see up here at the top of the image, now here's another split reflection that appear. If I jump again to the next reflection, the next image, so that apparently split reflection now merges into one reflection. So again, so this is, I don't know what's going on there, but it doesn't bode well for the quality of my crystal. And if I keep going through the images, a few more elongated reflections keep appearing, like here is another one there, that the split reflection merging into one bigger reflection again. So again, this is no good. And every time you see something like that, elongated and split reflections, this is a good idea to discard the crystal and screen some more. Now, let me go back to my own example here. Obviously, we don't see any of that here, so we are ready to jump to the pre-experiment phase. So don't click on pre-experiment right away, because otherwise you will put your data into the directory of the last person who used CrysAlis Pro. Instead, go to edit. It is important that you push on edit here so as to determine your own data directory. And so if you push the browse root folder, then you open up a window of File Explorer, and then you can create or travel to any existing folder that you may have already here. And then of course, at any level, you can add additional folder. So my advice is that you have a folder named after yourself. And then in there, you create additional folders for each one of your projects, knowing that in your project directory, CrysAlis Pro will create automatically an additional subdirectory named after the name that you will give to your experiment once you start your data collection. Last thing, for those of you who work in a multi-lab environment, I would also advise to create a directory with the name of the lab. So here I will choose that webinar folder, click OK, and just always make sure that the path here is indeed the one to the folder that you think you selected. Now, a couple more explanations about the panel that is just underneath. So these parameters are those used for calculating a default strategy at the end of the pre-experiment. So basically, when the pre-experiment finishes up, the strategy interface will automatically open up and a default strategy will be calculated for you. Of course, you can play with that strategy from there, but at least you will start with a pretty good default strategy. And those parameters here are the default ones that will be used to calculate that strategy. So the default should be on calculating a strategy to get a complete data set, 2.837 angstrom, which is the resolution limit to publish structures when the data has been collected with copper radiation. And the IFS sigma target value here is the one that your overall data should have. So basically, the strategy will also estimate the exposure time so that your overall IFS sigma, or the overall IFS sigma for your reflections, is 15. Now, for those of you who are more experienced about CrysAlis Pro and who are managers of the system, let me mention two more things. For any strategy that you select here, if you push on the setup button, then you can determine or change the target parameters used for that strategy. Then by clicking on that double arrow button here, you can also add or create any new strategy that you wish. For instance, from the pull down menu here, I had previously created a new strategy that is called MOF. And if I click on the setup button, here are the parameters that I set up myself. So MOF crystals are usually being weaker, so I implemented a resolution target here of 1 angstrom only, and I have a sigma target of 7 instead of 15. And I also implemented a type of strategy to be calculated by default to be not only complete, but complete and redundant, so that that panel appeared and I could set up my own target redundancy in there. So as managers of the system, or as more experienced people of CrysAlis Pro, you can set up all these kind of things if you want to. And then if you want, you can then tell your students, well, you know, from that pull down menu, choose that strategy to be calculated at the end of pre-experiments. So let me go back to the default I had before. Last thing before I push the start button is the exposure time is set at 0.5 seconds at the moment. Again, I didn't do that. CrystalLabs did it by itself and estimated that I have enough with a ½ second exposure time. This is based on the IFS sigma that was estimated from the screening images and the exposure time that was used for for those screen images. So here CrysAlis Pro is telling me you probably have enough with ½ second. If you're not happy with that exposure time, left click on that blue button and implement the exposure time that you wish. All right, so now I'm going to click on the exit and start the pre-experiment so that our pre-experiment images are being collected. So if you focus again on the live display of the goniometer, you see things moving here. You see the goniometer moving to get to a different crystal orientation. And if you look again in the main window of CrysAlis Pro, you see that we have already collected 2 runs, which means 2 different crystal data in 2 different crystal orientations. The goniometer is moving again here, set up a 3rd crystal orientation, and then data are being collected in that 3rd orientation. So there it is, 10 images were collected in that 3rd orientation. So the pre-experiment here collected data in 3 different crystal orientations, and for each crystal orientation, or for each run, 10 consecutive images were being collected. And like I told you it would do, CrysAlis Pro automatically opened up the strategy interface. Now let's set aside that strategy interface at the moment, and let's rather look at the results from the pre-experiment. On the right-hand side, just like what happened during screening, a concurrent indexing took place also during pre-experiments. And so new or updated unit cell parameters have been calculated. Turns out that they are the same as what was already obtained in during screening. But again, remember, it doesn't have to be as such. Sometimes after screening, your unit cell parameters might still be slightly wrong because you just don't have enough data yet. However, at this moment, it is critical that these indexing be correct, because you're going to calculate your strategy according to those unit cell parameters, and therefore they must be correct. So make sure that you have a percentage now of index reflections that is pretty high. So here I've got 100%. It doesn't have to be exactly 100%, but I like to see at least 85 to 90% there. And make sure also that the number of reflections from which that percentage number is calculated is high enough. So at least 15 to maybe even 20 reflections at this point is desirable, because if you have too few reflections, well, then those numbers, the unit cell parameters are not really reliable. So enough reflections, enough strong reflections, 15 to 20 would be nice, and a high percentage number of reflections indexed. After you have made sure of that, then go look at the reciprocal space. Now, the reciprocal space, that sounds like something scary. Don't worry about it. You don't have to fully understand what it is at the moment for those of you who are more beginners, but at least let me tell you what to look for in that reciprocal space. So to open the reciprocal space viewer, push the Lattice Wizard button, and then push on the Ewald Explorer reciprocal space button. So it's better to view the reciprocal space along one of the preferred orientations, along one of the reciprocal axes, A star, B star, and C star. So they are not A, B, C, they are A star, B star, and C star. So if I click on A star, here is a better orientation. Those dots here represents reflections, and the grid represents the lattice calculated from those unit cell parameters and displayed in the reciprocal space. So those dots here are pretty small and there are only few reflections, so I can increase the size of those dots by going to the up here to the GUI settings button. Left click on it and choose, and I will choose here to display the reflections according to their intensity, F of I. Then okay. So now those circles represent or are proportional to the size of the circles is proportional to the intensity of the reflections. So a successful indexing must absolutely show that the reflections coincide with the crossing points on that grid, those crossing points being also called lattice points. And you want to see a perfect overlap between the reflections and the lattice points in all directions, or all three directions of the reciprocal space, so along A star, B star, and C star. So here, obviously, everything checks out just fine. So I can get out of the reciprocal space. Let me show you again a couple of examples of things that are not desirable to see. Here is a data set where only 62% of the diffraction pattern was indexed. So if I look at the reciprocal space here, here is what it looks like. Let me, now I have many more reflections than in the previous case. So let me go back here and decrease the size of those reflections. So here there are a bunch of reflections that indeed coincide with the lattice points, but I also have a lot of reflections in between lattice points along that axis. So let me remove those from the display, the reflections that have not been indexed and those that are in between lattice points. See, these are called the wrong reflections in the table at the bottom right here. So I remove those from the display, and you see that the index reflections are actually beautiful. They all coincide beautifully with the lattice points. It's just that I've got something more. And that something more comes from the second diffraction pattern, and that second diffraction pattern comes from a second component within the crystal. Turns out that this crystal was twinned. And when you see something like that, your first reflex should be to discard that crystal and screen some more, hoping to find a crystal that will show one single and clean diffraction pattern. Now, that twin was also particular because the additional reflections are along that axis here, the vertical axis. It doesn't have to be that way. So additional reflections may appear randomly in between lattice points, right? They don't have to be only along one of the axes. So this is one example. And let me show another one with which I want to make a certain point here. So you see here, 100% of the reflections were indexed, and yet something was wrong. If I go to the reciprocal space, what I see in the reciprocal space is split reflections, okay? So here it was also a twinned crystal, but the two twin components, or the two diffraction patterns, were really close to each other, almost on top of each other. So as a result, all the reflections appear close enough to the lattice points, although they are not on top of it, but they appear close enough to the lattice points for CrysAlis Pro to still think that they were properly indexed, and therefore my 100% reflection, percentage reflections indexed. Whereas I know that as a crystallographer, that one row of reflections should be indexed in one lattice, and the second row of reflections should be indexed in the second lattice. But again, if I had only trusted the numbers, I would have never found out that there was a problem with that crystal. Okay? So again, if you see something like that, discard the crystal and screen some more and see if you can at least find a better one. At least try. So now let me go back to my to our example of the day. And so nothing of this nature for our crystal here. If I look at the reciprocal space, everything just checks just fine. Okay. So now I can close the lattice wizard, and the strategy interface comes back up. Before we start the data collection, or it will push one of those start experiment button, I will first close the strategy interface. Because right now we've looked at numbers only, and at the reciprocal space, you also must look at the images. Always look at the images as well. And just like I did for screening, so I will use this button at the bottom here to browse from one image to the next. From the Starburst button, you can also adjust the contrast to see things a little bit clearer, maybe, although here didn't make much of a difference, but so. So basically, like I explained before, now you want to see reflections that are as close as possible to the edge of the detector, and you can browse through all your images to make sure that you have reflections closer to the edge of the detector, away from the beam stop, from the direct beam position around which those resolution rings are centered. And here, obviously, we've got a strong reflection here beyond at about 0.9 angstrom, and we have others even further. So this is good. So again, reflections spread out through most of your detector area. And then single reflections, remember no split reflections, and reflections that are not too elongated. So it's always a good idea to also look at your diffraction images. So now I'm ready to go back to the strategy interface. I'll explain briefly what that strategy interface shows, and then I'll start the data collection. And that will be basically the last part of our webinar. Before to do that, we'll take a second short break, and Joe is going to ask you a second poll question to ask you what kind of operating system you use. Basically, CrysAlis Pro runs on Windows, but you can still run it on your Mac or Linux computers by installing a virtual Windows machine. So we want to know whether you guys know about that, and so what operating system you use on your computer. Go ahead, Joe.
I've launched a poll, and again, the question is, what platform do you run CrysAlis Pro on? And the first answer is my computer is Windows-based, or I have a Mac and run CrysAlis Pro in a Windows virtual machine. And the last answer is I have a Mac and did not know CrysAlis will run only on Windows or on Windows virtual machines. So we've got about 78% of the people voted. We're now at 80. We'll let it go another few seconds. And we'll stop right at a minute. Oh, a few more people chimed in. Well, pretty much most of the people, in fact, do use Windows, 89%, with a handful of people running on a Mac using a virtual machine, and then one person did not realize they could run CrysAlis Pro on a virtual machine, a Windows virtual machine on a Mac. So thank you very much. We'll stop sharing and continue.
All right, thank you, Joe. So just remember that if you don't have a Windows machine per se, don't feel like you can't use CrysAlis Pro. Just install a Windows virtual machine. So now I'm going to tackle the strategy, and to do that, I first have to reopen the strategy interface, and to do that, I go back to the Start/Stop button here, and then select Recalculate Strategy. So as I do that, File Explorer opens up and asks me, so which experiment do you really want to reopen? Make sure that you are in the correct directory. You can always see the path to your images by looking at the top here, the top band above the image, and then double click on the preexp.run file. This is the file that determines your pre-experiment and contains all the information for it. So double click on it. And then, so as I do that, the strategy interface will open up just in a handful of seconds. So what do those numbers mean? So first, a strategy has been calculated to reach a complete data set. Remember, that was the default that was set up in the pre-experiment dialog. That the plot here at the bottom indeed shows us that we should get 100% completeness. This is the plot in red using the strategy that was just calculated. In blue, we have the redundancy that our data will end up with. So it's just as such, right? But remember that that method basically calculated only a strategy to get the complete data set. And once the data set was or reaches its completeness, then it turns out that the predicted redundancy will be 3.3. So that the strategy for a complete data set was calculated with or using the lattice found upon indexing by CrysAlis Pro, which is at the moment primitive orthorhombic. OP stands for primitive orthorhombic, and this is orthorhombic because those three angles are real close to 90 degrees. So that completeness is directly related to the lattice of your crystal, and that completeness is calculated to 0.837 angstrom, which is again the resolution limit that was input as a default in the pre-experiment dialog. So to get to that complete data set, the program is telling me that it wants to collect 870 images in 15 runs, meaning 15 different crystal orientations. If you want to have a look at these runs, you can click on the button that says Edit Run List, and here you have the details of all the runs calculated by the strategy algorithm. So now the exposure time here has been automatically calculated or estimated by the program also at something super short, 0.12 second. And this is to get to a I have a sigma target of 15. Again, that was in the pre-experiment dialog as a default. And according to the I have a sigma that the program estimated for the reflections calculated during the pre-experiment, the program now is telling me that with 0.12 seconds, the overall I have a sigma of my data set should be close to 15. By the way, this is the I have a sigma on the individual reflections before any kind of merging of the symmetry related reflections and the friddle pairs is done. So at this point, you are welcome to push that button, start named experiments. Let me make a couple more comments. For some of you students, your managers or your PI might ask you to always collect in TrackClinic. To do that, for the low A group here, the pull down menu for the low A group, open up the pull down menu and select 1. Okay, so that is the nomenclature or the notification for the symbol rather for the low A group that would be that for primitive TrackClinic. So primitive TrackClinic is the lowest symmetry possible in the lattice, and that means that most of your reflections are not symmetry related with others. Okay, so if as a result more of the reflections are unique, they are not symmetry related with anything else, and therefore you have to collect more of those reflections. Basically, you have to collect all the unique reflections to get to a complete data set. So if you need to collect more reflections, you'll need to collect more images. And here is the demonstration. Since I changed the lattice here, I have to calculate a new strategy. You see, you couldn't start an experiment anyway because the start experiment buttons have become grayed out. So you can't miss it. You have to calculate a new strategy. And now the program in that very low symmetry wants me to collect 2,574 images in 38 scans. And again, that's because I need more images because I need to collect more of the reflections coming out of the crystal. So again, if your managers want you to collect in TrackClinic, no worries. Open up the pull down menu here, select 1 and calculate new strategy. Now let me go back to what we had before. And I will make a couple additional comments for those of you who are more experienced crystallographers. So you can certainly play with the resolution limit if you wish here. If you implement a new resolution limit, then you also have to calculate a new strategy. If you have a chiral molecule or you're in a non-central symmetric space group, you may want to get an absolute structure, and for that you need to keep the friddle pairs separate. For that, uncheck that box. See, if the box is checked, then the friddle mates are considered equivalent and therefore they will be merged. Whereas if you have a chiral molecule and need an absolute structure, you need to keep the friddle mates separated, so therefore you need to uncheck that box. And that is usually combined with having a data set that is more redundant. And to do that, open up that pull down menu here and choose a different strategy mode. So instead of selecting complete, then you will select complete redundant. And as I select that, you see that that additional panel opens up and I can implement my target redundancy here. Of course, then I have to calculate a new strategy. And then again, the program wants me to calculate more images because I have to collect more of those, or more often these reflections. All right, so, and I think that's all I wanted to show here. Let me go back to the default strategy we had before. Calculate again. And then I'm ready to start the data collection. Given the number of images that need to be collected and the exposure time estimated by the program, the CrysAlis Pro is also telling me that this experiment should last just 3 minutes. And as a result, it can also tell me when my experiment will be finished. So with all this information, you can basically even time your experiment, your data collection, to finish at a certain time. By the way, for the exposure time, here this was estimated by CrysAlis Pro, but you can certainly move that or change that at will to have your data collection finish a bit earlier or a bit later. So I'm going to push start experiment now, and let me make one more comment too. See, in that dialog for start named experiment, so first of all, I will implement my experiment name only now. That's the way I do it, because so this is only now that I deemed this crystal worth of data collection, and so this is only now that I enter a name for the data set that will be collected. And you should also enter here the chemical formula, or at least the chemical content of your crystal. This is because CrysAlis Pro, as data collection is ongoing, will do a concurrent data processing as well as a concurrent structure solution. Basically, there's a program called AutoChem that you can link to, that we provide, and that you can link to CrysAlis Pro. AutoChem itself is nothing but an automated version of OLEX2. Okay, and so as data collection goes on, once your the data set has reached a certain completeness, AutoChem will automatically open up and already try to solve the structure. And to do that, it's good that AutoChem knows of the chemical content of your crystal, and therefore it's good to enter at least the chemical contents there. Yep. So now I'm going to push start. The first thing that happens when you start the data collection is that pictures of the crystals are being taken. So you see here the goniometer is moving to bring the crystal perpendicular to the camera again. And now the program rotates the crystal along phi throughout 360 degrees. And an image of the crystal is taken every 6 degrees. That will amount to 60 images, and so you can use these images to do phase indexing afterwards. And then once those images are all being taken, then data collection start, and I will stop here. We can watch the data collection ongoing, and hopefully the structure appear on our screen at some point. Meanwhile, I can start taking some of your questions. So I'm sorry I went a bit long maybe. I gave quite a bit of details, but I still have a bit of time to answer some of your questions.
Hi, Pierre. So I answered a few questions during your talk. The last question remaining, is there an offline version of CrysAlis Pro just to process frames data on the hard disk?
Yep, absolutely. So as you install CrysAlis Pro, actually, both versions come together. Then even if you want to use CrysAlis Pro only for data processing, so an online version is also installed with. Of course, it doesn't bother your computer. So anyway, the data processing version is then installed on your computer. And by the way, it is license free and free of charge, which means that you can install it on as many of your computers as you wish, and this is all free. Okay, and so basically, if let me show the desktop here maybe, and you see all my icons here. I've got online version and red version here, red standing for reduction. So that's the how to say, shortcuts here, which are or the gray icon are for the online the processing only version of CrysAlis Pro.
And remember, you have to go to the forum and sign up, and then you can request your copy of CrysAlis Pro from there.
Okay, that was the only question remaining, Joe.
Any other questions?
So meanwhile, I can just point, just so that we see a structure here appear at some point. I can point as to how the goniometer moves, basically. So the data is always collected along a vertical axis, as you see it here now. So the whole bulk, the whole goniometer moves along that vertical axis. Once a run is finished, the goniometer moves along what is called the axis kappa and the little axis here in the middle, phi. So kappa and phi are used to orient the crystal in a certain way in the beam. And once the crystal is oriented, then the whole goniometer rotates along omega, which is the vertical axis. And then for the next scan, kappa and phi will change again to bring the crystal yet again in a different orientation in the beam, and a certain amount of rotation will be done along omega, the vertical axis, to collect the required number of images in that crystal orientation. And meanwhile, as I was talking, you see that now the structure of cytidine is being solved automatically by AutoChem from within Crystallizable. Okay, I think that's all I needed to say about this webinar today.
We have no more questions.
Okay.
Okay, well, thank you very much. Someone raised their hand.
Okay.
Doug, do you want to ask a question?
Can you hear me?
Yeah, we can hear you.
Okay, yeah. Could you tell me something about that detector you have there? I mean, we have the Eiger, but on this one, I don't see any banding at all, and it's a lot wider, right?
Correct.
And you
Pierre,
have
do you want to?
You have all that fancy blue lights on the top of it too.
Go for it, Joe.
Sure. So what the blue lights are telling you is the speed at which the data is being collected. And I don't remember what your Hertz rate was, Pierre.
No, I
you
don't
set
remember.
that up. But you can see when it's going slowly, it's idle and moving between scans. When it speeds up, it's telling us that it's collecting image data. The faster that goes is the faster the image data is coming off. It will operate up to 70 Hertz. It's made up of 3 sensor modules. So maybe, Pierre, if you change the contrast a bit.
I'm afraid I'm at the maximum contrast already.
Okay, so there are actually 3 panels there, Doug, and if you look carefully along about 1.78 angstroms, you can see there's maybe a little bit of a break there, and that's one gap.
So here, actually, you see that resolution rings at 1.78 angstrom is broken down because there's a gap here, and the same, okay, you maybe can't see it, but I see it directly on my screen here. There's the second gap there where my red cursor is located right now. So there is the second gap there.
So this is the Highpix Arc 150, and it covers 150 degrees in one setting. It is our high-end detector for the home lab.
Thanks.
So do you remember the Rapid at all? So that was a curved image plate detector, and so this detector uses the same sort of technology in a sense of you curve around the sample to collect data more efficiently.
Okay, thank you.
Thank you, Doug. Let's see. Any other questions? Oh, wait, we have 2 more. What's the easiest method to unwrap all the diffraction patterns after the experiment is complete to produce one big 2D image of a complete data set?
Yeah.
We might have to take that one offline because I don't quite understand it. There are ways of doing, making a 3D image, one big 3D image of the complete data set, but I'm not sure about one big 2D image.
So this is probably this older feature in the Lattice Wizard unwarping here. Maybe that's what this person is talking about. But this is essentially replaced by the Ewald 3D here that reconstructs your diffraction pattern in 3 dimensions. So we rather use that one now rather than a 2D unwarping of the images.
Oh, so you're asking for a procession. Got it. Unwrap confused me. Okay.
Maybe that's what this person is asking, right?
Okay. Yeah. Okay. All right. So we've answered that. And then the next question is, with the curve of the detector, can we still be able to change the sample to detector distance?
Absolutely.
And the answer is yes. The minimum distance is 42 millimeters. The radius of curvature is 62 millimeters, and you can change it to the maximum limit of the crystal detector distance. The software understands the difference in distance and properly predicts and integrates the reflection positions. Any other questions? Okay, well then, thank you very much. Thank you for your time. Be safe and have a good day, afternoon, evening, morning, whatever you're going to enjoy. Thank you and bye.
Thank you, everybody.